section 2.1, rates of change and limits. So we have a graph of, what graph is that? It's just sine. So we have the sine function, and we're labeling that f of t. And I've drawn your attention to the area between t and t plus h. And so the distance between my two vertical lines is h. And the first thing we want to do is find the average rate of change between the 2 points on the function. Okay. There are certain key terms that we use all year long. When you hear this, you must think this. When you hear average rate of change, you must think this. Average rate of change is just this. It is a very commonly asked question on AP response problems to find the average rate of change, and you should do a little dance if that's what they ask, because that's very straightforward. Just find the slope between the points. All right, so I want to write in notation the slope between these 2 points. So I didn't give you any exact numbers. All right, so what would I call this point here? If the function is f of t. F of t plus h. And this one, which is the f of t. All right, and our xi is our t and t plus h, obviously. So if I needed to find the average rate of change between these two, what would I write? Change in, average rate of change is flipped, so we're just talking change in y over change in x. And the change of y would be f of t plus h minus thank you. F of t all over. We could write t plus h minus t, right? But it's just equal to h. Well, not yet. So what this is called, this is an average rate of change. It is also called the difference quotient. Sometimes you will see this called the difference quotient. It's missing one thing to be the derivative, which we'll get to in just a second. That's not easy. Okay, so this is sometimes called the difference quotient. It is the average rate of change. All of those mean slope. That's all we're doing. Okay? So it's very easy for us to find the slope between 2 points. We've done it since algebra 1. Well, things get a little more interesting in calculus because I am going to be interested in the rate of change at f of t alone. So I won't have 2 points to find my slope. So the rate of change at f of t alone would be the slope of the what line? It is the slope of the tangent line that we're going to be looking for. So let's take a look at this problem going a little bit further. We'll do one more example here with just our finding the average speed. Speed is a rate of change. All right. So we have a problem where a rock breaks loose from the top of a tall cliff. What is the average speed during its first 2 seconds of fall, given that free fall is modeled with 16 feet squared? So right now I want you to find the average speed from time 0 to time 2 on your paper. And we get what? A little louder.
32.
Thank you, we get 32. Just a calculation of slope using the function that we've given. And what were our units? Feet per second. Okay. All right. So now let's look at instantaneous rate of change or instantaneous speed. That is the rate of change at one instant, where we no longer have the two. All right? So if we look at this example again, we'll just go to there. We want to find the speed of the rocket in example 1 at the instant t equals 2. Okay? Well, if we think about this, I have on my graph, so this is 16t squared. I have 2, and then I have some change in my time h. So we have 2 plus h. All right? Well, I could approximate the instantaneous rate of change at 2 by doing the slope between 2 points, between 2 and, let's say, 3. Okay? How would my approximation be? Would it be good? It might be too fast. It might be too fast, yeah. And it wouldn't be the closest I could get. All right? Well, how could I get closer to the slope at 2? Make it smaller. All right, so I could move to 2.5 and find the slope between 2 and 2.5. And I'd have a better approximation. How do I get better? We move closer and closer and closer. So, right now what I want you to do is to fill in our table. So this is numerically finding or approximating the instantaneous rate of change at 2. So we have f of 2 plus h minus f of 2 over h. And I want you to calculate that when h is 1, when h is 0.5, 0.1, 0.01, and 0.001. So let's split this up so everybody doesn't have to do all of them. So Ben and James, do 1 for me, please. Michael's table, do 0.5. Michael F. Let's go with ladies, do 0.1. Okay, Hadley and Megan and Marlo. Let's have Karen and Mason and Tim do 0.01, and Kristen and Leah do the last one, please. When you've got it, let me know and I'll put it in my table. Remember, our function is 15t squared. So our h is 1, so we're doing f of 3 minus f of 2 over 1. Ben and James, what do we get? What do we get? 80. Change my color. How about my 0.5 people? Do we have it? Okay. Any others? 0.1? Yeah.
AMR is 0.01.
0.01 here.
64.16.
64.06. Give me one more.
1.16.
Oh, 1.6?
Yeah.
Is there another decimal place or no? No, just 0.160? That's what we got too. Okay. And you guys are saying oh, 0. 64.016. 0.1? What is it? 65.6. 65.6? Gotcha. 0.5? All right. So we see a trend happening. What does it look like our average rate is approaching?
64.
Looks like it's going to get closer and closer to 64. So that's our numerical approximation. Remember, we look at things graphically, numerically, analytically, and so on. All right, well, what are we actually doing? What are we looking at when we keep moving this closer and closer and closer? Louder? Thank you. We're looking for the limit. All right. So the instantaneous rate of change is the limit of the average rate of change as h goes to 0. So it is the limit as h goes to 0 of that difference quotient. Now, Daisy, what is that called?
The derivative.
That's the derivative. All right, other names for derivatives would be instantaneous rate of change, and we also said it was the, what else? Slope of the tangent line, slope of the tangent line. When I got hired out of college at an engineering firm, one of the interview questions was, do you know what a derivative is? And then they followed that up with, do you know what an integral is? And they weeded people out by the incorrect answers to those two questions. So I can't tell you how many times they came in after I was hired and said, oh, somebody else, no idea what a derivative is. Nobody knows, they don't know what an integral is. It's just kind of funny, kind of pops up. So these things, these words are important. We know a derivative is the slope of the tangent line or the instantaneous rate of change, the rate at one instant instead of the rate between two instants. Okay? All right, are we okay with this page? Let's continue. Yes, may I continue or are we still writing? I see some writing going on. Let's move on. All right, so we did find the limit of the average rate of change numerically. We talked about how we could approximate it graphically by moving our second point closer and closer and closer to h. Well, now we want to find it algebraically. All right, our f of t is 16t squared. So literally now we want to take the limit as h goes to 0 of that difference quotient. We are finding the derivative algebraically. All right, so what is f of 2 plus h? Notice I am writing my limit. Do not drop off your limit. It needs to be on every line. How do I evaluate f of 2 plus h? 16 times 2 plus h squared minus 16 times 2 squared all over h. All right. So what do we need to do here? Be able to, if I plug in right now, what do I get? We get a 0 over 0, our indeterminate form. So now what? Little louder? Yes. Boil and solve and cancel it where we can. So I've got 16 times, if I FOIL it out, what do I get? 4 plus, how many h's? 4h. Quiet vote. 4h plus h squared minus what's 16 times 4? 16 times 4, 64? Yeah. Yep. All right. And when we multiply through here, we get 64 plus 64h plus 16h squared minus 64 all over, my lines are not so good, all over h. What do I need in front? We're taking a limit as h goes to 0. All right, what happens? 64s are gone. We should factor it out first. So let's factor out our h out in front, leaving me with 64 plus 16h all over h. Now it can happen. Our h's will cancel. And we're taking the limit as h goes to 0. And what do we get? 64. So, we have just algebraically found the slope of the tangent line when t equals 2, instantaneous rate at t equals 2, the derivative at t equals 2. Questions there? Nope, we're good? All right, moving on. Oh, nothing to do there. All right, now, at your desk, calculate it out, please. As we work with these limits, quiet, please. It will be to your benefit to simply know a couple of limits so that you can look for them inside other problems, and it will help you solve them. Okay? So right now, the two that I want you to find are the limit as x approaches 0 of sine x over x, and the limit as x approaches 0 of 1 minus cosine x over x. Okay, so graphing calculators out, just graph these. You can zoom in around 0, but you'll be able to tell what our y value is approaching. Okay? Our limit as x approaches 0 of sine x over x is equal to what? It is approaching 1. So as I say here, this is a special limit that is helpful in finding many other limits. It is something that you can look for within a problem that deals with trigonometry, sine, cosine, tangent. You just need to know it. Okay? All right. Does anyone have our limit as x approaches 0 of 1 minus cosine x over x? That one is 0. So big stars here, we need to know these. Life will just be easier. All right, let's move on. All right, instead of going through every single property of limits, we're just going to do examples that illustrate these properties so we get our practice with solving limits while we talk about the properties. All right, so in our heads, when we see a limit, our first thing that we try is what? Plug it in. So when I see the limit as x approaches 2 of x cubed minus 2x plus 5, if I'm just going to plug in that 2, then really what I'm doing is the limit as x approaches 2 of x cubed minus the limit as x approaches 2 of 2x plus the limit as x approaches 2 of 5. All right, this is the addition and subtraction property, that the limit of a sum or difference is equal to the sum or difference of the limit. We could do them one at a time. You don't have to write it out this way. You can still just plug into each, but we should know that the limit of this polynomial is equal to the limit of each of its terms added and subtracted together. And what do we get? Here I have 8. Here I have 4, and then plus, what's the limit of a constant? A constant is just a horizontal line, so it will be that constant. So what do we get? Someone say it. Thank you. We get 9. All right? Number 2, we have the limit as x approaches 1 of 3x squared. And what I'm trying to show is the constant multiple property. So this is the same as 3 times the limit as x approaches 1 of x squared. So if we have a constant multiple, it can be pulled out from the front and multiplied by your limit of what is left. So this would be 3 times what? 1 squared, or just 3. All right. Our next one is the product property. The limit as x approaches -1 of sine of x times cosine of x can be performed by doing the limit as x approaches -1 of sine x times the limit as x approaches -1 of cosine x. What do we get? This is a free response question. Any form of the correct answer is correct. So we could write this as sine of -1 times cosine of -1. That's an acceptable form of the answer. Don't be thrown off. We can take the sine of a -1, but remember the value of sine and cosine bounces between 1 and -1. All right. Finally, our quotient property. The limit as x approaches -2 of 6x to 6 over x plus 3 can be solved by doing the limit as x approaches -2 of 6x to 6 over the limit as x approaches -2 of x plus 3. But we need a little domain restriction. X cannot equal what? -3. Thank you. All right, and what do we get? You guys figure this one out for me. I've got the bottom. You do the top. What is that? -32 times 6? Negative? Correct? Is it 192? What is it? 32 times? Yeah, 192. All right. So there's our little review on limit properties. I might have another property or two. We'll see. Any questions on what we did there? All right. Now let me be clear. You need to be aware of these properties. You do not have to always write out the limit of 6x to the 5th over the limit of x plus 3. We still just plug in, but we need to know that these properties are why we can simply just plug in as we go. Okay? Any questions on this? Yeah.
Can you go back up to the first one?
I see that. Is that good? I don't like them having a little headings without anything on them. We good? Okay. All right, let's move on. So, this one is out of your book. Determine the limit as x approaches 0 of tan x over x. Well, when we plug in, what do we get? We get 0 over 0 indeterminate form, which means we need to change the look. How can I change the look? Yeah, so tangent can be written as sine of x over cosine x. All over x. Little louder.
That should be sine of x over x cosine x, which then we can make 1 over cosine x.
We can change it as x approaches 0. And think about our special limit that we ran into. What's that special limit? Sin x over x. So this is the limit as x approaches 0 of sin x over x times, and what did you say, AJ? 1 over? Yep. Okay, so we can now look at these limits separately. Times the limit as x approaches 0 of 1 over cosine x. And what is this one? That is 1. That's the one we just graphically looked at. And how about this one? Thank you, Keegan. Also 1. Cosine of 0 is 1. 1 over 1 is 1. So our limit is equal to 1. We're good? Yes.
That'd be equal for, like, one was 1 and the other was 1, or you multiply?
You just multiply it.
Okay.
Yep. If that came out to be 4, it'd be 1 times 4.
Got it.
Yep. All right. Let's see what else we have. So we talked about this. We keep seeing this 0 over 0. And that is an indeterminate form. We need to change the look. All right. Well, what if we end up getting a number over 0? So in this one, the limit is x approaches 3 of x squared minus 2 over x minus 3. So write that down. And when we plug in, what do we get?
Is that x minus 3?
It's x minus 3 on the bottom, yes. That's a minus. What do we get on top? 7 over 0. So we have this situation where it is undefined. Well, when we end up getting a number over 0, the limit will not exist. That is an undefined situation. The limit does not exist, and there are 3 possible things that could be happening. It could be that as we get closer and closer to 0, so what you can do is evaluate numerically and what that means is I am approaching 3, so maybe I want to see what is happening at 2.999, and maybe 2.99, and maybe 3.001, and 3.01, and plug these values into our expression to see what it's approaching. So the 3 possibilities of what could happen is that this one's getting huge, and this one's getting huge. Both sides are going to infinity. So the limit could be approaching infinity, but we need to say and understand that that is still a does not exist situation. Okay? The second thing that could happen is this one could be getting huge in the negative, and this side could be getting huge in the negative, so it would be approaching negative infinity, but that is still a does not exist situation. Or what could happen is this side is going to get huge positively, this side is going to get huge negatively, so we've got a situation like this going on, and that, the 2 limits are not going the same direction, we just simply say it does not exist. Okay? All of them fall into a non-existent limit, but this is more information being provided. We have a visual in our head if we know it's going towards infinity and does not exist. We can think that they're both going like the volcano curve. Okay? Or like the negative volcano curve. So it's just providing more information. So when you see this, for me, I want you to write does not exist going towards infinity. Or does not exist going towards negative infinity. Or does not exist. Now, on the AP test, they will not have, on a multiple choice option, they will not have infinity and does not exist as your option. They will give one or the other, okay, on your multiple choice. So they will never confuse you by putting both of those on there.
What is the case for number 3?
Number 3, so if I draw my little pictures, number 3 would be if it's going kind of like that and like that. From the right, it's getting huge into positive. From the left, it's getting huge into negative. So this one would be something like this. And this one would be something like this. Does that help? All right. So that's when we have a number over 0 instead of 0 over 0, or one of our other indeterminate forms that we'll talk about later. Am I good to move on? All right. Now, our last thing that we need to talk about is called the sandwich theorem. So let's take a look at what it says first. It says if g of x is less than f of x, which is less than h of x, for all x not equal to c. So we're interested in what's going on at c, so we're looking everywhere around it. In some interval about c, then, and the limit of g of x as x approaches c is equal to the limit of h of x as x approaches c is equal to L. Then, the limit as x approaches c of f of x will equal L. So that's a lot of words. The picture is more helpful, I think. So we have a situation where we have h of x, and g of x is less than h of x everywhere, and f of x is between the two everywhere in our interval. Okay? Well, then if the limit as x approaches c here for h of x is 5, and the limit as x approaches c of g of x is 5, then what must be the limit for f of x as x approaches c? It is sandwiched in between them. This is also called the squeeze theorem. Okay? Then the limit for f of x would also be 5. Okay? So if the outside functions have the same limit, then the one in between will have the same limit as well. A good number of limits are proven using the squeeze or sandwich theorem. We don't use it too much, but you should be aware of it. And I have a little example to show you next. So you should be aware, the delta epsilon limit definition is not actually an AP topic. It is not tested on the AP test, but all of you will probably be taking more math, and it is the basis of many proofs in mathematics. You need to be aware of it when you move on to your next math class. Okay. And on the AP test, you won't be asked to prove something with the sandwich theorem, but again, you need to be able to be conversant in it and have seen it. All right, can I move on? Just some writing. All right. So you don't need to copy this one down. You can just look up and watch. Sorry, my equations did not come out very clearly. But let's take a look at this example of the sandwich theorem. So we have these three funny functions. Now, we can turn the light off. It might help. Just a little. All right. So we have these three functions where f of x is 2 root x minus 1 minus 1. That one is less than the rational function, which would be our g of x in this case. And that is less than our e to the x minus 2, which would be our red one. Okay, so we clearly have a setup for the sandwich theorem. And if this is true, if this is always less than this, which is always less than this, and I want to figure out the limit as x approaches 2 of this expression, well, I can take the limit of each expression in my little inequality. The limit as x approaches 2 of f of x is going to be less than the limit as x approaches 2 of g of x, which will be less than the limit as x approaches 2 of h of x. Well, we can calculate these limits, correct? Just plug in. So when I plug in here, I get 2 minus 1 is 1, square root of that is 1. So we get 2 minus 1 for 1. And then over here, if I evaluate this limit, 2 minus 2 is 0, e to the 0 is 1. Well, if the limit of this one is 1 and the limit of this one is 1, then what do we know about this one? The limit of that is also 1. So just a basic look at the squeeze theorem. Make sure I didn't have anything else for you here. All right. Hold on, we thought I put our homework on there. And that is it. So let me bring up the homework from the website.